Welcome to the session. Myself M.Hariprabhu, EEE department. Today we are going to discuss about the topic DC drives. So in this DC drives, in the last class we discussed about a single phase fully controlled rectifier fed DC drives. So after that, now we are going to discuss about a three phase controlled rectifier fed DC drives. So before going to this topic, a brief introduction for this three phase controlled rectifier fed DC drives. There is a for large power DC drives, three phase controlled rectifiers are used. The three phase controlled rectifier circuits which gives more number of voltage pulses per cycle of supply frequency. So this makes the motor current continuous and filter requirement also very less in this three phase controlled rectifier fed DC drives. So the number of voltage pulses per cycle, which depends on the number of SCRs present in this circuit. So the semiconductors and fully converters are most commonly used in this device. So the dual converters are used in reversible drives having power ratings of several megawatts in steel industry and heavy applications. So these are the applications we have to use in dual converter. So more to the topic, the three phase fully controlled converter fed DC drive. So this three phase fully controlled converters which is used in industrial applications up to 1500 kilowatt drives. So it is nothing but a two quadrant converter. The average output voltage is either positive or negative, but the average output current is always positive. This is the main point. So it's nothing but a two quadrant converter. So if it is a two quadrant converter, the average output voltage is either positive or negative. Okay, but at the average output current is always positive in this two quadrant converter. Okay, so here we have to use 6 SCRs, that is T1, T2, T3, T4, T5 and T6. We have to use 6 SCRs here, and then V is nothing but the average output voltage, and I is nothing but the average output current. Okay, R is the armature resistance, L is the armature inductance, EB back EMF. Okay, so separately excited DC motor, so we have to give the external supply to this field, that is VF. Okay, and then field current is IF. So this is the two quadrant converter. Here the voltage is either positive in first quadrant, and then the voltage is negative in this fourth quadrant. Okay, so that only in this voltage is either positive or negative, but the current is always positive in fourth quadrant as well as in first quadrant. Okay, so here there are two groups of SCRs are present. One is positive group, the another one is the negative group. So here the SCR T1, T3, T5, that is here T1, T3 and T5 which represents the positive group, and T4, T6 and T2 which represents the negative group. Okay, so the positive group SCRs are turned on when the supply voltages are positive, and the negative group SCRs are turned on only when the voltages are negative. Okay, at the time of negative voltage supply, the negative group SCRs are turned on. So at the time of positive voltage supply, the positive group SCRs are turned on. That is T1, T3, T5 are the positive group, and T4, T6 and T2 are the negative group SCRs. So in this it is for alpha equal to 60 degree, there is the alpha, and then T1 is turned on. For example, T1 is turned on at pi by 3 plus 60 degree, that is pi by 3 plus alpha. Here alpha equal to 60 degree, so pi by 3 plus 60 equal to 120 degree. That is T1 is turned on 120 degree, and T2 is turned on at omega t equal to 180 degree, and T3 at omega t equal to 240 degree, and so on. So each and every 60 degree one SCR will be turned on. So this is the main important thing in this SCR turn on process. So when T1 is turned on at omega t equal to 120 degree, so T5 is turned off, and T6 is already conducting. So as T1 and T6 are connected to R and Y respectively. So when T2 is turned on. So at the time T6 is commutated. So as T1 and T2 are now conducting, the load voltage is VRB here. Okay, so this is the output voltage waveform. That is if T4 and T5 is conducting, so at the time the output voltage is here. First the output voltage is VBY. T4 at the time of T4 and T5 conduction, the output voltage is VBY. At the time of T5 and T6 conduction, the output voltage is VRY. At the time of T1 and T6, the output voltage is VRB. At the time of T1 and T2, the output voltage is VYB. So at the time of T2 and T3, the output voltage is VYR. So and then T3 and T4 is turned on, so the output voltage is VBR. And then T5 and T4 is turned on, so at the time the output voltage is VBY. So each and every 60 degree the one ACR will be turned on. So first is T4 is already turned on. So after 60 degree T5 is turned on. Okay. So after 60 degree T6 is turned on. So after 60 degree T1 is turned on. Okay. The remaining previous ACRs will be in turn off condition. Okay. So after 60 degree T2 is turned on. So and then after 60 degree T3 is turned on. And then after 60 degree T4 is turned on. And then after 60 degree T5 is turned on. And then after 60 degree T6 is turned on. Okay, like that the ACRs will be turned on each and every 60 degree. Okay. So for alpha equal to 120 degree, T1 is triggered at omega t equal to 180 degree. That is after 60 degree of alpha, the T1 is turned on. Okay, and then T2 is triggered at omega t equal to 240 degree and so on. So each and every 60 degree one ACR will be turned on. The output voltage waveform that is as shown in this figure. Okay. So the average output voltage is negative, which means that DC voltage is delivering the power to AC source. Okay, so this operation is called a line commutated inverter operation. For alpha equal to that is in the range of 0 to 90 degree, this converter operates as a rectifier. That is a rectification mode. That is in this rectification mode, the power flows from source to load, and then in the angle alpha, in the range of 90 degree to 180 degree, the converter which operates as an inverter, that is an inversion mode. Okay, so in this inversion mode, the power flows from load to source. Okay, so it can work in the inverter mode only if the load has a direct EMF E. Okay, so it is a regenerative braking mode. Okay, from alpha equal to 0 to 90 degree, it acts as a rectifier. Okay, and then 90 degree to 180 degree, the converter operates as an inverter. That's all. Okay, so in this rectification mode, the power which flows from source to load, and then the inverter mode, the power flows from load to source. Okay, so this is the firing sequence. If the SCRs are numbered as shown in the figure, so in this firing sequence is first 1 2 and then 2 3 and then 3 4 and then 4 5 and then 5 6 and then 6 1. First one T1 and T2 will be in the conducting state. So after 60 degree T1 is turned off, so T3 is turned on. Okay, so after 60 degree T2 will be turned on, T2 will be turned off, and then T3 is turned on, and then T4 is also turned on. Okay, next T3 will be turned off, and then T4 will be turned on, and then T5 turned on now. Okay, like that 5 6 and 6 1. Okay, so for the delay angle, there is alpha equal to 120 degree, the motor voltage becomes negative. So that is from alpha after 90 degree. Okay, so after 90 degree, the motor terminal voltage becomes negative. So this is nothing but the inversion mode of operation. Okay, at the time the converter operates as an inverter. So the time the power can be transferred from motor to the supply. Okay, if the motor voltage is reversed with a reversing contactor or by reversing the field current. Okay, so this is known as the regeneration mode. Okay, so at that time, this regeneration mode, the motor speed will be automatically decreased due to the power feedback. So thus the motor voltage will decrease, because in this inversion mode the motor voltage is decreased. That is the motor terminal voltage is negative in the range alpha greater than 90 degree, that is for example alpha equal to 120 degree, the motor voltage becomes negative. Okay, so the speed is reduced in this regeneration mode. So the motor, if the speed is reduced due to this power feedback, the motor voltage also decrease. So this is the output voltage waveform, and then is a small expression, that is the average motor terminal voltage, which is given by VA equal to 3 by pi in the range alpha pi by 6 plus alpha to pi by 2 plus alpha. Okay, VAB d omega t equal to 3 by pi in the integration of root 3, that is VAB equal to root 3 Vm sin omega t plus pi by 6. Okay, VAB equal to root 3 omega m sin omega t plus pi by 6 into d omega t. Okay, so after simplifying this expression, and then we have to apply the limits, that is the upper limit is pi by 2 plus alpha and the lower limit is pi by 6 plus alpha. After integration we have to apply the limits, that is upper limits minus lower limits, we get the average output voltage is VA equal to 3 root 3 Vm by pi. Okay, so after that 3 by pi kept as it is, and then root 3 Vm equal to Vm L cos alpha. Okay, so the final output voltage is, average output voltage is VA equal to 3 VML by pi cos alpha. This is the average output voltage. And then the motor speed we have to calculate now, that is the motor terminal voltages equation we already know, that is VA equal to EB plus IA RA. In this equation we have to substitute EB. Okay, EB equal to Km into omega m, that is Km we have to write here, and then instead of omega m we have to write pi n. Okay, plus IA RA. Okay, so after that the equation becomes VA equal to Km pi n plus IA RA. So next we have to rearrange this equation, we get the speed, that is the motor speed, n equal to VA minus IA RA divided by Km pi. This is the motor speed equation. We have to calculate this motor speed equation in this motor terminal voltage equation. Okay, so next is the speed torque characteristics. So in this speed torque characteristics, this is, in this mode it is a motoring mode and this is a braking mode. Okay, so in this braking mode we have to vary the alpha, the motor speed also varied. Okay, so decreasing the alpha, automatically the motor speed also decreased. So if you have to increase the alpha, the motor speed also increases. Okay, in this motoring mode the motor speed increases by varying the alpha, that is alpha is increased. Okay, so in this braking mode the alpha gets decreased, so at the time the speed also gets decreased. Okay, so in this separately excited motor the torque T equal to Km pi Ia. Okay, normally torque is directly proportional to pi Ia. By removing the proportionality we write Km. Okay, torque T equal to Km pi Ia. Therefore n equal to in this previous equation, we have to write Ia by pi. Here n equal to VA minus IA RA Km pi. So in this speed equation we have to substitute VA by Km pi minus RA divided by Km pi. We have to substitute this torque. Okay, that is torque Ia equal to Km T by Km pi. We have to substitute Ia equal to T by Km pi. Okay, so we get the motor speed is VA divided by Km pi minus RA divided by Km pi square into T. Okay, that's all about this speed. So this is the final motor speed equation for this 3-phase fully controlled rectifier fed DC drives. So that's all about this operation of this 3-phase fully controlled converter fed DC drive. So the next topic is dual converter fed DC motor drive. So this is nothing but it is operated in 4 quadrant. Okay, so first quadrant, second quadrant, third and fourth quadrant. So it operates on all the quadrant. So dual converter is also called as a 4 quadrant converter. So which means the output voltage and output current is either positive or negative. So in some of the quadrant the output voltage is positive and some of the quadrant the output voltage is negative. Okay, but others and then similarly the output current is positive in some quadrant, the output current is negative in some of the quadrant. Okay, so only we get the output voltage and output current is either positive or negative. So the dual converter, which consists of the two similar single phase or three phase fully controlled converter. Okay, so it is connected in parallel at the input side. In this input side is nothing but the AC side, and are connected inverse parallel at the output side. Okay, so in the input side here single phase or three phase supply, we have to give the converter A. So in this converter B, that is the AC can be converted to DC, okay, by using this converter A, and then in between this converter A and converter B, we have to connecting the circulating current limiting reactor. So after that the DC current can be given to the converter B, and then the converter B can be converted to DC to AC. Okay, so this is nothing but the single phase dual converter. Here in the converter A, you have to use the 4 ACRs, and the converter B, you have to use another 4 ACRs. So here the converter A, which operates as a rectifier, and the converter B, which operates as a inverter. Okay, so from alpha equal to 0 to 90 degree, the converter A operates. From alpha equal to 90 degree to 180 degree, the converter B operates. Okay, so this is a single phase dual converter. We have to give the single phase AC supply to the converter A. The converter A, it can be used to convert the AC supply into DC supply, and then the DC supply which is given to the circulating current limiting reactor. So in this the field is there, so the field current is IF. So after that the converter B, so we have to give the DC supply to this converter B, and then in this converter B the DC supply can be converted to AC by using this converter B. Okay, so in this converter B, which acts as an inverter, so at the time the firing angle vary from 90 degree to 180 degree. So okay, so this is nothing but the three phase dual converter. Here we have to connect 4 ACRs in one converter, and here we have to connect 6 ACRs in a single converter. Okay, because this is a three phase AC supply we have to given, so 3 legs are there, so only we have to connect 6 ACRs in this converter A as well as converter B. Okay, so in this conventional fully controlled rectifier operation at a continuous current mode, the average output voltage, which is equal to 2 root 2 V cos alpha divided by pi. This is for single phase, and then 3 by pi VLM cos alpha. This is for three phase connection. Okay, so by varying the delay angle alpha, it is possible to vary the output voltage, whether it is either positive or negative. You have to vary the output DC voltage. Okay, but the output current is always positive if any one of the converter is in the operating state. Okay, so using the dual converter, we can have the following two operations of mode. One is the variable speed motor in forward and reverse direction. The another one is reverse and forward braking of motor. So these are the two modes of operation by using this dual converter. One is variable speed motor in forward as well as reverse direction. The another one is forward and reverse braking of motor. Okay, these are the operating modes in this dual converter. So these are the voltage and current quadrant diagram. That is first quadrant, second quadrant, third quadrant, fourth quadrant. So the dual converter which operates in all the 4 quadrants. So there are 2 modes of operation. One is non-circulating current mode, the another one is the circulating current mode. Okay, so in this non-circulating current mode of operation, so at any instant only one converter is in the operating condition. Okay, so in the circulating current mode, either both converter A and converter B is operating at a same time. But in this non-circulating current mode, at any instant only one converter is in the operating mode, that is either a converter A or converter B. Okay, here there is no need circulating current limiting reactor, because at any instant only one converter is in the operating state, so there is no need of circulating current limiting reactor. Okay, so in the first case, when converter A alone operates, so at the time the current flows from X to Y. Okay, so when the firing angle, which is varied from 0 to pi by 2, this is not 2 by pi, this is pi by 2, that is alpha A equal to 0 to pi by 2. So the machine operates as motor in forward direction. So in this forward direction the motor rotates, so at the time the converter which operates as a rectifier. Okay, that is the firing angle varied from 0 to pi by 2, the motor operates as a rectifier. Okay, the motor in the forward direction, the converter which operates as a rectifier. Okay, so after that the firing angle which is varied from pi by 2 to pi. Okay, 90 degree to 180 degree. So at the time the machine operates in this reverse braking mode. So in this reverse braking mode the motor speed is reversed. Okay, so if the motor speed is reversed, the converter which operates as a inverter, that is a line commutated inverter. Okay, when converter B alone operates, this is the second case. Okay, in the previous case converter A alone operates, but now the converter A is in the off condition, the converter B is in the on condition. So when converter B is alone operates, so in this mode the average DC current is always flows from Y to X. In the previous mode it flows from X to Y, but now the DC current flows from Y to X. So when the firing angle which is varied from 0 to pi by 2, so the alpha is nothing but when converter B operates, the alpha, it represents alpha B, that is 0 alpha B to pi by 2. So that is the alpha B which is varied from 0 to pi by 2. So at the time the motor operates as a that is the machine operates in a reverse direction, the converter B which operates as a rectifier. Okay, so and then if the firing angle is varied from, next the firing angle which is varied from pi by 2 to pi. Okay, next case, at the time the machine operated in the forward braking mode. Okay, if the converter B is operated, so at the time the firing angle is varied from 0 to pi by 2, the motor rotates in reverse direction, so the converter B operates as a rectifier. But now the firing angle varied from pi by 2 to pi, so at the time the machine is operated in the forward braking mode. Okay, so the converter B which operates as a line commutated inverter. So when the direction of motor is to be reversed, so at the time it is required to see that the first converter is turned off when the motor has attained 0 speed, and then the current becomes 0. So afterwards the second converter is made to operate by giving the suitable signals to this second converter gate pulse. Okay, to achieve this current is to be sensors and also a small time interval which is required for changeover of the converter. Okay, so this is the voltage and current quadrant diagram. So in this first quadrant the converter A is operated, so at the time it operates as a forward motoring mode. So the converter A which operates as a rectifier, in the firing angle which is varied from alpha A is varied from 0 to pi by 2. So in this first quadrant converter A alone operates. Okay, so now in the second quadrant the converter B is operated, the converter A is in the off condition in the second quadrant, the converter B is alone operated. Okay, so in this converter B is operated, so at the time it converter which acts as an inverter. So now the mode is changed to forward braking mode, the motoring mode to change to braking mode, that is the forward braking mode. At the time the firing angle alpha B which is varied from pi by 2 to pi. Okay, this is the operation in a second quadrant. And then in this third quadrant the converter B is in the operating condition and the converter A is in the off condition. If the converter B is in the operating condition, so the converter which acts as a rectifier, that is in the rectification mode. So in this rectification mode the motor is in the reverse motoring mode. Okay, that is the in this reverse motoring mode the firing angle alpha B which is varied from 0 to pi by 2. Okay, this is the operation in this third quadrant. And then fourth quadrant there is a converter B is alone operated and then converter A is in the off condition. So in this converter B operating condition, so the converter which acts as a inverter, so at the time the motor operates as a reverse braking mode. So the firing angle alpha A which is varied from pi by 2 to pi. So this is the fourth quadrant operation. So that's all about this quadrant operation, first quadrant, second quadrant, third and fourth quadrant operation. So on this the small derivation, the circulating current mode, so both converter A and B will be in the operation throughout. Also at the DC side that is 3 by pi VLM cos alpha A. Okay, this is the our average output voltage in the converter A operating condition. Okay, and then the converter B operating condition, that is minus 3 by pi VLM cos alpha B. So the 3 by pi VLM get cancelled in this both left hand side and right hand side. So cos alpha A equal to minus cos alpha B. So we have to write the minus cos alpha B equal to cos pi minus alpha B, that is 180 degree minus alpha B. Okay, so after that we have to write alpha A plus alpha B equal to pi. So in this alpha a plus alpha b equal to pi, we have to write alpha b equal to pi minus alpha a. This is the firing angle for this converter B. Okay, so the firing angle of converter A and converter B are controlled such that the average DC output voltage at the terminal X and Y due to this converter A and B should have the same value. Okay, for achieving this, if alpha A equal to alpha, then alpha B equal to pi minus alpha. Okay, so in case 1, we have to operate first quadrant and the second quadrant operation. Okay, so and then case 2, the third quadrant and the fourth quadrant is in the operating condition. Okay, so here in the first case, the converter A firing angle. So in this case condition, so at a time converter A is operated and the converter B is also operating condition. Okay, so here the converter A firing angle which is varied from 0 to pi by 2. So at that time the converter B firing angle varied from pi by 2 to pi. So it likes that the firing angle varied from 0 to pi by 2. The converter A operates as a rectifier, and then converter B, the firing angle which is varied from pi by 2 to pi. So the converter which operates as an inverter. Okay, so the converter A operates as a rectifier and the converter B operates as an inverter. Okay, so the machine which acts either as a motor in forward direction, that is the first quadrant, which is fed from converter A, or as a brake in reverse direction feeding to supply through converter B, that is in the second quadrant. Okay, so in this case 2, third quadrant and fourth quadrant operation, so here that is the opposite of this case 1, that is nothing but the converter B firing angle varied from 0 to pi by 2. In the previous case, converter A, the firing angle varied from 0 to pi by 2, but in this case the converter B firing angle which is varied from 0 to pi by 2, and the converter A firing angle varied from pi by 2 to pi. So here the converter B operates as a rectifier and the converter A operates as a inverter, that is the line commutated inverter. Okay, this is in the third quadrant and fourth quadrant operation. Here in this first quadrant, that is if the converter A operates as a rectifier, there is a firing angle varied from 0 to pi by 2, that is alpha A varied from 0 to pi by 2, and then converter B acts as an inverter, that is firing angle pi by 2, alpha B varied from pi. Okay, so that is in the forward motoring mode. This is the first quadrant operation. In the second quadrant operation, that is the converter A operates as a rectifier and the converter B operates as an inverter. Okay, so here the converter A, the firing angle varied from 0 to pi by 2, and then converter B firing angle varied from pi by 2 to pi, that is alpha B. Okay, so in the second quadrant the motor operates as a forward braking mode. So in this third quadrant the converter A operates as an inverter. Okay, and then converter B operates as a rectifier. If it is an inverter mode, the firing angle alpha A varied from pi by 2 to pi, and then rectifier mode, the firing angle alpha B varied from 0 to pi by 2. So the motor operates as a reverse motoring mode. This is the third quadrant operation. So in this fourth quadrant operation, the converter A operates as an inverter and then converter B operates as a rectifier. So if it is operates as an inverter, the firing angle alpha A which is varied from pi by 2 to pi, and then converter B operates as a rectifier. If it is a rectifier, the firing angle alpha B which is varied from 0 to pi by 2. So the motor which operates as a reverse braking mode. So the DC machine operates either as a motor in reverse direction taking power through converter B, that is the third quadrant, or as a brake in forward direction feeding power to the mains through converter A in the fourth quadrant. So this operation, this is known as the fourth quadrant operation, that is four quadrant operation. So the real converter which operates in all the four quadrants, so it is known as the four quadrant operation. For this both converter operates so in current continuous mode. Okay, so now we are going to discuss about the comparison between the circulating current mode of dual converter and non-circulating current mode of dual converter. So first, in this circulating current mode, the current limiting reactor is required and to limit the circulating the current. Okay, so in this non-circulating current mode of dual converter, the current limiting reactor is not required because at any instant only one converter is operated. Okay, so only the current limiting reactor is not required in non-circulating current mode. The second point, the triggering angles of converter A and converter B are dependent on one another, that is alpha A plus alpha B equal to pi. So if alpha A is varied, or alpha B is also varied. Okay, So in this non-saturating current mode, the triggering angles are not dependent, because at any instant only one converter is operated. So if alpha is varied, it does not depend on alpha B. So the triggering angles are not dependent on only one converter operates at a time. So the third point is, it is easy to maintain continuous current mode operation of converters. In this non-circulating current mode of dual converter, to maintain the continuous current mode of operation, load parameters are to be altered. So, and then the next point is the circulating current mode. Reversing the direction of rotation of motor is easier in this circulating current mode, because there is no need to sense the current zero condition as a circulating current limiter. And then in this non-circulating current mode of dual converter, this reversing the direction of rotation is possible by changing the operation of converter from A to B or from B to A. From this, current zero is to be sensed and there exists a small time lag due to this. Okay, so in the circulating current mode, the dynamic performance of the converter is very good, better. Okay, and then but in this non-circulating current mode of dual converter, the dynamic performance is poor, because at a time converter A is operated and the converter B is also operated. Okay, and the sixth point, since the both converters are in the operation, losses are more and efficiency is less. And this non-circulating current mode of dual converter, the losses are less and the efficiency is better in non-circulating current mode. Okay, because at any instant only one converter, either converter A or converter B is in the operating condition, so the losses are very less and the efficiency is better if losses are very less. So the next topic is chopper fed DC drives. So chopper fed is chopper is nothing but it can be used to convert fixed DC to variable DC. Okay, so the DC motor speed, it can be used to control through this DC chopper. It is nothing but a switching circuit. DC chopper, it can be used to convert from fixed DC to variable DC. Okay, so the fixed DC voltage is fed to this DC chopper circuit. So here the DC chopper can be used to convert fixed DC to variable DC voltage. So this variable DC voltage, which is fed into this DC motor drive, by varying this DC voltage, the motor speed can be controlled. Okay, here the self-commutator device we have to use in this DC chopper is a MOSFET, and then power transistors, and then IGBT, then GTO, and then IGCTs. So these are the self-commutator devices are used for building the choppers, because they can be commutated by low power control signal. Okay, and they do not need a commutation circuit. It can be operated at a high frequency for the same rating. So that's all about the chopper introduction. And this is the advantage of DC chopper control. If you are move on to the chopper, there is some advantage. There is high efficiency, and then flexibility in control, then lightweight, then small size, then response is very quick, and then regeneration down to very low speeds. So these are the advantage of DC chopper control. And then application of DC chopper drives is battery operated vehicles, and then traction motor control in electric traction, and trolley cars, and then hoist, and then electric braking. So these are the application of DC chopper drives. So now we move on to the types of DC chopper drives. In this we have 5 types. First one is first quadrant chopper or type A chopper, and then second quadrant chopper or type B chopper, and then the third one is 2 quadrant type A chopper or type C chopper. Then fourth one is 2 quadrant type B chopper or type D chopper. Then fifth one is 4 quadrant chopper or type E chopper. In this the first and second types are operates only in a single quadrant, either first quadrant or second quadrant. But in third one and the fourth one is, it can be operated either, it can be operated both quadrant, that is either first and second or first and fourth quadrant. Okay, so in this fifth type, it can be operated in all the 4 quadrants. So it can be also called as a type E chopper. So this is nothing but the 4 quadrant operation of chopper. Okay, so now we move on to the first topic, and that is a first quadrant chopper or type A chopper. Okay, these are motoring chopper. So in this, Vs is nothing but the source voltage, and then this is a transistor, and there is a freewheeling diode. It can be improve the performance, and then the current in the continuous form. So you have to use this freewheeling diode here. V is nothing but the average output voltage. This is the motor. RA is the armature resistance, L is the armature inductance, C is the back EMF, I is the average output current. So this is the circuit diagram for this type A chopper. So here the current limiting control which is used in this chopper. So in this current limiting control, the load current is allowed to vary between the two limits, that is the upper limit and the lower limits. Here the upper limit and lower limits, the upper limit is IA2 and the lower limit is IA1. Okay, so the on and off times of the chopper which adjust automatically when the current increases beyond the upper limit. So in the beyond the upper limit, the chopper is turned off, so the load current freewheels and starts to decrease. Okay, when it falls below the lower limit, the chopper is turned on, the current starts increasing in the load. So the load current IA and the load voltage VA waveforms which is shown in figure. So the next, the lower the ripple current, higher the chopper frequency. Okay, so the discontinuous conduction avoid in this case. So because it is only in the continuous conduction, we have to use this freewheeling diode. So only the current should be in the continuous form. So the current limiting control is in the superior one. So during this on period of chopper, there is a T on period, the duty interval is 0 to T on. The T is varied from 0 to T on. So the motor terminal voltage VA is source voltage VS, and the armature current increases from IA1 to IA2. So the operation which is described by, so that is the equation, voltage equation is IARA plus LA DIA by dt plus EB equal to Vs. So at the time of 0 to T on, the source voltage is Vs, that is the output voltage, and then chopper is turned off at T equal to T on. So at the time T equal to T on, the chopper is turned off. So during this off period of chopper, the freewheeling interval, that is T on to T. So in this T on to T, the output voltage is 0, that is the terminal voltage VA is 0. Okay, so the described equation is RAIA plus LA DIA by dt plus EB equal to 0. In the previous case it is Vs, but now in the interval of T on to T, that is the voltage equation which is equal to 0. So VA equal to 1 by T integral of 0 to T on Vs dt. This is the average output voltage equation. Here we have to apply the limits from 0 to T on, because we have the source voltage Vs in the limit 0 to T on. So we have to take this the limit, that is 0 to T on. 0 to T on, I have to take this, that is Vs by T. So after integration, we have to apply the limits from 0 to T on, that is Vs into T on by T. Okay, so T on by T is nothing but there is the on period by total time. Total time is T equal to T on plus T off. That is on period is nothing but T on. Okay, that is T on by T, which is equal to the duty cycle. Okay, so if the duty cycle is varied, the motor speed is also varied. So VA equal to del into Vs. We have to write T on by T equal to del into Vs. We have to write either del or alpha. Both we can be used to represent the duty cycle. Okay, and then we know the motor terminal voltage equation, VA equal to EB plus IARA. So del into Vs, VA equal to del into Vs, substitute here, and then after substituting this VA equal to del into Vs, we have to rearrange this equation. We get IA equal to del into Vs minus EB by RA. So and then we know this back EMF equation, that is EB equal to Km into omega m, and then torque equation T equal to Km into IA. So in this torque equation we have to write IA equal to T by Km, that is EB equal to, we know Km omega m equal to VA minus IRA. So in this VA minus IRA equation, we have to substitute IA equal to T by Km in this equation. Okay, so we have to equate these two equations, this Km omega m equal to VA minus IA. Instead of IA, you have to write T by Km into RA. So we get the speed omega m equal to VA by Km minus T by Km square into RA. Okay, so this is the omega m equation, omega m equal to, now we have to write VA equal to del into Vs. So here del into V, okay, divided by Km minus RA into T divided by Km square. This is the motor speed equation. So the next one is second quadrant or type B chopper. This is only operating in the regenerative braking mode. So it is operating in the second quadrant. So this is regenerative braking of a separately excited DC motor, which is fairly simple and it can be carried out down to very low speeds. Okay, so in this regenerative braking mode, it can be carried out only down to very low speeds. Okay, so in this regenerative braking mode, the energy of the load may have to be fed to this supply system, the DC motor which works as a generator during this mode, because it is in the regenerative braking mode. So the DC motor which acts as a generator. So as long as the chopper is on condition, So mechanical energy can be converted into electric energy by the motor. So now it's working as a generator by increasing the stored magnetic energy in the armature circuit inductance, and it is a remainder which is dissipated in this armature resistance and a transistor. When the chopper is off condition, a large voltage occurs across the load terminals. So here this IA1 is the minimum current and IA2 is the maximum current. So this is the upper limit and this is the lower limit of this current limiting control. So this voltage which is greater than the supply voltage Vs, and the energy stored in the inductance and the energy supplied by the machine which is fed back to the supply system, because it is in the regenerative mode. So the machine is fed back to the supply system, and then the voltage which is load falls to Vs. The diode in the line blocks the current flow, which is preventing any short circuit of the load. It can be supplied to the source. Okay, so from the time t on to t, the output voltage is Va. Okay, from 0 to t on, the output voltage is 0. Okay, it is in the regenerative braking which is achieved here by changing the direction of current flow. So a small derivation. During this energy storage interval from 0 to t on, the motor terminal voltage is 0. Okay, so the armature current increases from IA1 to IA2, that is the minimum current to maximum current. During this duty interval t on to t, the motor terminal voltage is Va. The armature current decreases from IA2 to IA1. Here in the limit t on to t, the current decreases from IA2 to IA1. But in this 0 to t on, the current increases from IA1 to IA2. Here the average output voltage Va equal to 1 by t integral of t on to t Vs into dt, Vs by t, t on to t. Have to integrate this equation. After that we have to apply the limits from 0 to t on. We get 0 to t on, and then that is Va equal to Vs into 1 minus t on by t. Okay, already we know what is t on by t is nothing but a duty cycle. Okay, that is on time by total time, t of plus t on equal to t. So you have to write t on by t equal to del. So 1 minus del into Vs you have to write as a average output voltage equation. Then Eb equal to Km into omega m, torque T equal to minus Km Ia. Why I have to write is minus is the Ia is reverse because it is in the regenerative mode. So you have to write minus Km into Ia. So E equal to Km omega m equal to Va minus Ia Ra. So we have to equate these two equations. We get omega m equal to Va by Km minus T by K. So you have to write this equation Ia equal to minus T by Km. So you have to write minus T by Km into Re divided by Km. So that is the final equation is omega m equal to 1 minus del into Vs divided by Km plus Ra by Km square. So in this numerator K, it comes to denominator, that is Km by Km into Km, that is Km square. Okay, so I have to write Ra by Km square into T. Okay, so this is in the speed torque characteristics. It is in the motoring mode and that is in the regenerative braking mode. So if alpha is increasing, the speed also increasing in this motoring mode. If the alpha is decreasing, the motor speed also decreases in this regenerative braking mode. Okay, so and then the third one is third and fourth one is 2-quadrant chopper drives. So it can be classified into two types. One is 2-quadrant type A chopper drive and then another one is 2-quadrant type B chopper drive. So first one is 2-quadrant type A chopper drive. Here the circuit diagram which consists of 2 chopper and 2 diodes, that is CH1, CH2 is chopper and D1 and D2 are the diodes. So it can be operated in both the quadrants. One is first quadrant and another one is the second quadrant. In this first quadrant, the chopper 1 and the freewheeling diode is in the operating state, and the second quadrant, the chopper 2 and diode 2 is in the operating state. The remaining chopper 1 and the freewheeling diode is in the off condition. Okay, this is a 2-quadrant operation which is also called as a 2-quadrant type A chopper drive. So here one is a forward, it operates as a forward motoring mode and then forward braking mode. In this forward motoring mode, when chopper CH1 is in the on state, so the supply voltage is fed to the motor terminals and therefore the armature current increases. So here the voltage and the current is always positive, therefore the motor rotates in forward direction. When the chopper is in the off state, so the IA which freewheels the diode D1 here, the IA which freewheels the diode D1 and therefore the IA decreases. Okay, so it is the forward motoring mode. This is the first quadrant operation. Okay, in this second quadrant operation, that is in the forward braking mode. So in this forward braking mode, the chopper 2 is in the on state. The second quadrant, the chopper 2 is in the on state, and diode 2 is also in the on state. Okay, so the motor acts as a generator because it is a braking mode. So the motor acts as a generator and the IA current increases. So due to this, energy is stored in this armature inductance. So this is the waveform. IG1 and IG2 are the gate pulse which is given to this chopper, and then V is the output voltage, and then IA is the output current. Okay, so when chopper CH2 is the off state, so the diode D2 gets turned on, and therefore the armature current IA is reversed. If the diode D2 gets turned on, it is in the second quadrant operation. So in this mode, the output voltage is positive and output current is negative. So in this second quadrant operation, the output voltage is positive. So in this both quadrant, the current voltage is always positive, but the current is positive in first quadrant, the current is negative in this second quadrant. Okay, in this second mode, the current is negative. In this first mode, the current is positive. Okay, so it is also called as a forward regenerative braking mode. So now the fourth type is two quadrant type B chopper drive. So this type of chopper drive which provides a forward motoring mode and a reverse regenerative braking mode. So here we have to use same two chopper, that is CH1 and CH2, and then two diodes D1 and D2. So it shows the two quadrant type B chopper drive. So two diodes and one is DC motor we have to use here. So this type of chopper which operates in first quadrant and fourth quadrant. So in this chopper it will be operated in first quadrant. In first quadrant, and the voltage and the current is positive, but in this fourth quadrant the voltage is negative but current is positive. So in this type of chopper drives, the current is always positive, but the voltage it can be varied from positive or negative. Okay, so in this first mode, there is a forward motoring mode. When the this forward motoring mode, the chopper 1 and the chopper 2 is in the on state. So at the time the motor rotates in the forward direction. So when the motor rotates in the forward direction, the IA current is increased. That is the armature current increases. When chopper 1 is in the off state, so the now the current flows from CH2 and diode D1. So here the output voltage and output current is always positive in this first quadrant, so which gives the forward motoring mode operation. Okay, so in this forward motoring operation, the duty cycle del which is varied from 0.5 to 1. So it is in the range of 0.5 to 1. So and then the second mode is a reverse braking mode. So when the chopper CH1 and CH2 are in the off condition, so the now current the flows from diode D1 and D2. So here the output current is positive but the output voltage is negative. But in the previous case the output voltage is positive, but now it is in the fourth quadrant, so the output voltage is negative. So here the power flows from load to source. We can achieve this in this mode as a reverse braking mode. So it is a fourth quadrant operation. Okay, here the motor speed which can be controlled by changing the duty cycle of the chopper. So in this reverse braking mode, the duty cycle which is varied from 0 to 0.5. But in the previous case, that is the forward motoring mode, the duty cycle which is varied from 0.5 to 1. But now the reverse braking mode, the duty cycle which is varied from 0 to 0.5. So this is the output voltage waveform. IG1 and IG2 is the pulse which is given to this chopper, and then VA is the average output voltage, and then I is the average output current. So in this first case, CH1 and CH2 is in the on condition, and then after that the CH2 is in the off condition, and the diode D2 is in the on condition. So after that CH1 is in the on condition and then CH2 gets turned on. Okay, so the diode 2 is in the off condition in this particular period. So now the fifth type is 4 quadrant operation of DC chopper. So here we have to use 4 type of choppers: CH1, CH2, CH3 and CH4, and 4 type of diodes are used: D1, D2, D3 and D4. Okay, so here the average output current is I0 and then average output voltage is V0. This is the DC motor part. In this DC motor part, as usual, we have to mention the armature resistance, armature inductance, and then the back EMF. This is the DC motor part. Okay, so this is a circuit diagram for the 4 quadrant operation of DC motor. So here we have the 4 quadrant. In this first quadrant, it is in the forward motoring mode. The second quadrant, forward braking mode. The third quadrant, reverse motoring mode. Then fourth quadrant, reverse braking mode. Okay, so in this first quadrant, the voltage, output voltage and output current is always positive, and then in the second quadrant the current is negative but the voltage is positive. But in the third quadrant, both current and voltage is negative. In this fourth quadrant, the voltage is negative but the current is positive. Okay, so in this first quadrant the chopper 1 is in the operated, so at the time the chopper 1 and the chopper 4 is in the on condition, that is the chopper 1 here. This first quadrant is forward motoring mode. So the first forward motoring mode, initially the CH4 is kept on, so at the time CH3 is kept off, and CH1 is operated. With CH1 and CH4 is in the on condition, so at the time the load voltage which is equal to the supply voltage, that is VA equal to VS. Okay, so here the load current is IA, the load current which represents IA, which begins to flow. So here the output voltage VA is positive, and then load current IA is also positive, which gives the first quadrant operation. When CH1 is turned off, so at the time the positive current which freewheels through CH4 and then diode to which gives the both output voltage VA and the load current IA can be controlled in this first quadrant. So it gives the first quadrant which gives the forward motoring mode. And then the forward braking mode, here the CH2 is in the operating state, and then CH1 and CH3 and CH4 are kept off. With CH2 on condition, so at the time the current flows from L inductance and then CH2 and then D4 and then E. So during on time of chopper, that is CH2, the inductance L which stores energy. So when CH2 is turned off, the current is feedback to source through diode D1 D4. So note that at the time the voltage is E plus L into dI plus divided by dt, which is greater than the source voltage Vs, as the load voltage Va is positive and then load current IA is negative in this second quadrant, that is the second quadrant which gives the forward braking mode. Okay, so here the power flows from load to source, which gives the forward braking mode. So and then the third quadrant it is operated in the reverse braking mode. So here the chopper 1 is kept off and then the chopper 2 is kept on. So the chopper 3 is operated. So the polarity of the load EMF E, it must be reversed for this quadrant operation. So here the chopper 3 is in the on condition. So at the time the load gets connected to the source Vs. So the output voltage VA and the load current are negative in this third quadrant operation. So it is also known as the reverse motoring mode. So when CH3 is turned off, so the negative current which freewheels through CH2 D4. So in this way the output voltage VA and the load current IA can be controlled in this third quadrant. So the third quadrant which gives the reverse motoring mode. So and then the reverse braking mode. So here the chopper CH4 is in the operating condition, then other devices are kept off. So at the time the load EMF E must have its polarity reversed. So the chopper CH4 which is in the on condition, so the chopper CH4 is in the on condition, so at that time the positive current which flows through chopper 4, diode 2 and then inductance and E. So these are the current flows direction. So during the on time the chopper 4, the inductance L which stores energy. When chopper 4 CH4 is turned off, so at the time the current which is fed back to the source, so through this diode D2 and D3. So here the load voltage is negative. In this fourth quadrant the load voltage is negative, but the load current is positive in this fourth quadrant operation. So which gives the fourth quadrant operation. So this mode is also known as the reverse braking mode. So that's all about the fourth quadrant operation of chopper. Okay, so the next one is closed loop control of electric drive. So here the feedback loop in an electric drive, it can be used to satisfy one or more of the following requirements. That is the first one is protection, and second one is improvement of speed response, and the third one is to improve the steady state accuracy. Okay, this is a basic block diagram of the closed loop control system. Here in this closed loop control system we have to use a speed controller, power converter and then DC motor and then feedback loop. So in this power converter we have to give the external power supply. So here we have to get the feedback from this DC motor, that is the speed N, which is given to this comparator, and then the comparator which compares the actual motor speed and then reference motor speed, which gives the error signal, that is En, and then the error signal which is given to the speed controller. So this controller can be used to control the motor speed by using this power converter circuit. Here the error signal which is given to this power converter circuit. So here the firing angle which is varied, which can be varied, and then DC motor can be controlled by using this controller circuit. So this is the basic block diagram of the closed loop control system. So here the motor speed which can be sensed by the speed sensor, that is a tacho generator. We have to use this tacho generator to measure the speed. It is a feedback signal N, that is the actual speed. Okay, so the actual speed which is given to this comparator, the comparator can be used to compare the actual speed and then reference speed, that is NR. The error signal which En, which goes to this speed controller here, En. Okay, and then the speed controller which produce the control signal or control voltage EC. So this control signal which is fed to the power converter. So here the power converter can be changed according to the control signal. By changing the output voltage, the motor speed can be controlled. Okay, this is the basic closed loop control system. So and then now the particular control, that is the current limit control. Here the current limit control scheme which is employed to limit the converter and the motor current that is below a safe limit during this transient operation. Okay, so it has a current loop, that is here, it is a current loop with a threshold logic circuit. This is a threshold logic circuit which gives the current from this current sensor. Okay, we have to sense the motor current by using this current sensor, and then which is given to this threshold logic circuit. Here it is a 0 to maximum value current. Okay, so the feedback loop does not affect the operation of the drive. So during this transient operation, if the current exceeds the set maximum value here, if the current exceeds the set maximum value, and then the feedback loops becomes active. Okay, and then the current which is forced below the set maximum value, which causes the feedback loop to become inactive again. Okay, so this is the operation of the current limit control. And then the closed loop speed control, here we have to use current limit control and also the speed control. We have to use both the loops here. Okay, one is the inner loop. The inner loop is the current loop, and then the outer loop is speed loop. That is we have to sense the motor speed. That is the outer loop. So here it implies an inner current control within an outer loop. The inner current loop which is provided to limit the converter and then motor current. We have to combine the previous two methods in this single closed loop control. Okay, so here an increase in the reference speed omega m star, here the increase in the reference speed omega m star which produces a positive error. Here del omega m is a positive error. So at the time the speed which is processed through this speed controller and applied to this current limiter circuit, so which saturates even for a small speed error. Okay, so here the limiter which sets the current reference value here, that is I star. I star is nothing but the current reference value. I is nothing but the actual current which is sensed from the motor by using this current sensor. This is for the inner current control loop at a value corresponding to the maximum allowable current. Okay, so here when close to the desired speed, the limiter desaturates here. When limiter desaturates, so here the steady state is reached at the desired speed with some error, that is steady state error, and at current for which motor torque which is equal to the load torque, decrease in the reference speed omega m star which produces a speed error. So here the current limiter which saturates and sets the current reference I star. This is for inner current loop at a value of corresponding to the maximum allowable current. So here the drive deaccelerates in this braking mode at the maximum allowable current. When it is close to the required speed, the current limiter desaturates. Okay, so the operation which is transferred from braking mode to motoring mode. So at the time the drive settles at a desired speed and at a current for which the motor torque which equals to the load torque. Okay, in this drive application where the load torque which is able to provide the enough accelerating torque, so the electric braking need not to be used here. Then it also the current limiter has the characteristics. Okay, so that's all about the closed loop control. Here we have to use both a control in this single closed loop control. One is the inner loop, another one is the outer loop. In the inner loop we have to control the current, and then outer loop we have to control the speed. Okay, so now we are discuss about closed loop speed control scheme for armature voltage control and field weakening control. So here we have to use a armature voltage control scheme and a field weakening control scheme. Here we have to use same speed controller and then current limiter and current controller, then firing circuit. The firing circuit which can be used to control the this converter circuit. In this converter circuit, we have to give the AC supply to this rectifier circuit. There is nothing but the current controlled rectifier here. Okay, this is the motor. We have to sense the motor by using this speed sensor. This is the field, and then this is the AC supply which is given to this rectifier circuit. Also we have to use this firing controller, and then I have to control the field by using this field controller circuit. This is the back EMF reference. This is the back EMF which is sensed from this motor circuit. This is the voltage VA. By using this VA, there is a motor voltage equation, that is VA equal to EB plus IARA. So you have to write VA equal to EB plus IARA. You have to write here. Then IA we have to sense here, that is IA, and IA is multiplied with RA, and then RA which is given to this summer circuit. Okay, so this is the circuit diagram for closed loop control scheme for armature voltage control and field weakening control. For any large positive speed error, the current limiter saturates, and the current reference IA which is limited to a value, that is IM, and the drive current which is not allowed to exceed the maximum permissible value. Okay, so here the speed error which is corrected at the maximum permissible armature current until the speed error which becomes small, and the current limiter comes out of saturation. Now the speed error here, the speed error that is here. Okay, the speed error which is corrected at the maximum permissible armature current until the speed error which becomes small, and the current limiter which comes out of saturation. Now the speed error which is corrected, and IA which is less than the permissible value IM. For a negative speed error IA star which sets the 0, because IA star is no use when reference speed is increased again. Okay, which makes the error positive. So at the time we have to use this charged PI control, that is proportional integral controller here, so which takes the longer time to response. Okay, so now we have to examine the operation above base speed, that is when closer to the base speed, VA is almost which is nearer to the rated value, and the field controller which comes out of saturation. For this speed command, that is above base speed, the speed error which causes a higher value of VA. So the motor accelerates, EB increases. If the motor accelerates, so at the time back EMF EB increases, so the field error EF decreases. If the back EMF increases, the field error EF decreases. So at the time reducing the field current. If the field error decreases, the field current is also reduces. So thus the motor speed which continues to decrease until the motor speed becomes equal to the reference speed. Thus the speed control which is above the base speed is obtained by field control with armature voltage maintained the armature voltage which is maintained near the rated value. So in the field controlled region, the drive which responds very slowly due to the large value of the field time constant. So that's all about the closed loop speed control scheme for armature voltage control and field weakening control. Thank you.